Euler's number or Euler's constant. When you get into high school at some point, most likely maybe when you start to study exponential growth, so exponential functions, you will run into this number e. Now that number, maybe if you kind of paid attention to your scientific calculator, even if you were in elementary school, you maybe had noticed that it pops up on a calculator. So here I'm going to point it out right here. Okay, so in this calculator, and notice there's the little e. Okay, and if I hit this little e, it equals, I get this number. So Euler's number is a number, and it is an irrational number. So now we have seen irrational numbers before, where they typically will be written out as some kind of a constant symbol, okay, that we have. And the reason for that is because if it's irrational, then it's never ending and it doesn't have a repeating pattern. And so we can't really write it as a fraction, which would be rational. Now, some symbols that you have run into, I'm sure that you kind of run into pi, right? So you've seen this. You've seen, maybe the square root, let's say maybe the square root of 2. And these are actually all irrational numbers, and they do come up from something that we know of. So for instance, pi itself comes from circles. So if you take a circle, you take its circumference, so which is the measure all the way around, and then you take its diameter and you divide it, so you create a ratio between those, which is your circumference divided by your diameter. You will notice that this is going to give you pi. And I did a video actually on that showing, so I'll put up a link up above there if you want to see it. And now for the square root of 2, these square roots, where they kind of came from, you may remember triangles. So here I'm going to try to draw a triangle here, which might have hopefully the same sides. So let's assume that this is 1 and this is 1. And if you wanted to find what the length of the hypotenuse was, you may recall the Pythagorean theorem. And as you were studying this, you would find that this is actually square root of 2. And we needed to introduce these kind of radicals or the square roots, but they were also irrational, unless, it was the square root of, let's say, a perfect square. So we have seen symbols that we utilize in math. Now, the letter E, you don't typically use until you probably get into high school, and then you definitely might use it later on if you continue into math and sciences. Now, where does this letter E come from, and why is it so important? Unfortunately, for most teachers, it's going to be very hard to explain and convince you about this letter E. So for the moment, you might have to say, okay, I understand that this letter E is kind of like a pi. It's kind of like the square root of 2. It's maybe some irrational number, and it's of some importance. It must be of importance as it kind of landed on our calculator and it's always there. And it's true, and it is this number, which is 2.718281, and so on. Now, why is it so important? So I'll try to tell you. Well, some applications of it is that after you do study a little bit of math, you eventually will get to calc or calculus. And there, you're going to be interested in kind of the slopes of various functions, sometimes maybe called the gradient. And now you're going to be needing, okay, these actual slopes, okay, within calculus. And you will find that this constant e has, okay, as a function, if you create one, which is going to be e to the x, it's going to have a very interesting property, all right? And so you do have to have a little bit of trust that this letter E comes in, because now from calculus and the convenience of this constant, this Euler's number, is that it allows us to actually simplify our life in a lot of different applications which use calculus in some form. And one of the key ones, and I am very biased because I've studied engineering, and I know that there are numerous applications in engineering where Euler's number is super useful within calculus-based applications. Now, there are others. I mentioned that there's, exponential growth, for instance, okay, utilizes, okay, this letter E as well. And I'm actually going to use that exponential growth to try to show you, okay, how we come about this number and you know what it comes out to. And there's other applications. So radioactive, for example, you know, decay might be dependent on this particular constant E. So it comes out in nature quite a bit, and it makes our life a lot simpler. All right, so I know that it's not the greatest of convincing that you have to know this constant E, okay, as we know it as Euler's constant or Euler's number, but you have to have a little bit of trust that you will need it, just like you utilize pi and just like you might utilize radicals or square roots of some kind. Now, let's try to show, okay, this Euler's number. And by the way, you know, Euler was a scientist or a mathematician in the past. He wasn't the only one that ran into this kind of Euler's constant, but we named it after him. It is a bit of a coincidence. I think that they just, or he just used the letter E. Okay, I don't think he really named it after himself. But okay, for whatever reason, that's what we used. And we used it as a symbol because it's an irrational number. So let me now go back a little bit and remind you of this exponential growth so that I can kind of show you, okay, how this E, or at least one of the ways that this E comes about. And then later on, as you study math and sciences, you know, you will see that this E is going to be popping up and it's going to be pretty useful, especially kind of because of the fact of its slopes, okay? So exponential growth, you know, you may recall, so I'm going to write it out here. So it is 1 plus, okay, r, and then within here, okay, so this is going to be to the n. I can put up a link if you've forgotten about exponential growth and exponential decay. So this r is the actual growth, and it typically is a rate. So this is some kind of a rate of growth. And then this, okay, is this n is how many periods it might take, okay, to grow to a certain amount. So you do have to kind of be exposed to this. Now, the original kind of coming out of this constant E, actually, I don't think it was Euler, I think it was maybe Bernoulli, who was interested in kind of money and then what happens to money within 1 year, okay, if you play around with this rate of growth. So what I'm going to say here is that, okay, let's imagine, okay, so that you were starting off, let's say with $1, and somebody came along and said, you know, how much money would you have if the bank gave you 100% return after 1 year? Well, 100% of $1, you would say, well, I guess I'm going to have $2 because I had $1 plus it grew 100%. So I have now $2. And now the question was, well, that was within 1 year. Now, what if somebody said, okay, well, I'm going to split this. I'm going to say I'm going to give you 50%, okay, for the first 6 months, and then I'm going to give you 50% for the second 6 months. You know, so what would happen then? So again, so you would say, okay, well, I'm starting with $1. So 50%, okay, of $1 is 50 cents. So that's going to get me to $1.50 after 6 months. But now I'm going to get another 50% for the next 6 months. But now I'm starting with $1.50. So if I'm going to be starting with $1.50, now 50% of that is going to be 75 cents, which means that I would end up with $2.25. And you would say, wait a minute. So if I split that 100, okay, into 50% for the first and then 50% for the second, okay, so the first kind of, you know, semi-annually, I guess, then I get a quarter more. So now you might think, what if I continue this? If somebody said, if I take this 50 and I take this 50 and I keep splitting this, and I say, well, what if I gave you 25% for the first 3 months, and then I gave you another 25%, and then another 25%, okay, and so on. So 25 and 25, 25 and 25, which seems like it's 100. Is it going to be more again? And the answer is, it will be more. So you might think, well, if I continue this pattern and this is called compounding. So if I compounded more frequently, so if I broke these down more frequently, will this keep on increasing forever? And that was the question, I guess, that Bernoulli and others wanted to answer. So if I continue on and I keep breaking these things down, is it going to just get bigger and bigger and bigger? So within 1 year, am I going to get to infinity? So I'm going to get, infinite amount of money if I just keep breaking it down. And it turned out that the answer is no. It turned out that if you keep breaking it down, eventually you get closer and closer and closer to a particular number. And that number was Euler's constant. Okay? So this breakdown, I can model this, okay? So this division within. So what I can say is really what it is, you're starting with $1 plus, okay? And then you had, let's say, your rate, okay? So in this case, we got 100% in the beginning for 1 year. But, I'm going to divide this, and I'm going to divide it by n, where n is, how many times am I splitting this up, right? Am I splitting it 2 times, so it's 50%, 50%, 4 times, so it's 25 and so on. And then, I have to do this to the n because of the fact that I am doing it for every single period. So I run into, kind of this funky formula, but it looks very similar to an exponential growth formula where this r, so in our case, this was just 1. So if I do this, so this was just 1 over n to the n. And now the question is, if I keep breaking this down and I do it, let's say infinite amount of times, or I approach infinity, what will the answer be? And the answer, it turned out that it was our constant e. So 2.71 and so on and so on. So we would run into back and we would see this irrational number pop up. So that was kind of the original kind of swing for this constant. And then it started to creep up because it had amazing properties within math and sciences. And that's why it became so dominant that we started to use it quite often. Okay? Because it kind of comes up in natures and our modeling of nature by math. And now, so if I go back in here, now I just want to convince you and show you this. So what I ended up doing is I took this formula, so this entire formula, and I encoded it into a spreadsheet. All right, so I'm going to put it into a spreadsheet just so that you can see. Okay, so on the left-hand side, so what you see, that 100%, that's your R. Okay, so that's my return within that 1 year. And that 1 that you see there highlighted at the moment, that just means, that I took only 1, one time, 1 period. And what I've gotten is basically this. And here is the formula which is encoded. So this is what you see there on the screen. So it's 1 plus 1 represents the 100%. They're divided by n. And I'm just referring to that cell, and then it's raised to the n. So this is exactly what I have done. Now, let's see it, as I keep making this bigger and bigger. So we said that when n was equal to 2, notice we get $2.25. All right? When it was equal to 4, notice that, we get even a little bit more, 244, 1.4, and so on. And as you make this bigger and bigger, so if I make this 8, again it's bigger. If I again continue just to make it bigger and bigger, then it just continues. But, so now I'm going to, let's say, put, 1,000. And you will notice that, 2.71, starts to look like that constant E. And indeed, as I make this bigger and bigger and bigger, so here we go, it gets very close. And that's what it would equal. So that's what it comes. It came down to kind of playing with money and then seeing this around. And now, so just to show you, so in this spreadsheet, the exponential, so E, Okay, it's called exp. Okay, and then you can put here, and within here, so what you put is basically your rate. So this is raised to the exponent of 1. Okay, and that's what it's going to start to approach. Okay, as our n gets bigger and bigger. Now the interesting part is, which not always everybody mentions, but okay, so in general, if you have this formula, and this is your rate r, so in our case, our r was 100%. We change it to decimal, so it was 1. Okay, so if you have this, and this is r, now if it's 100%, then your answer is going to be e to the 1, which is basically e. So that's raised to the exponent of e, which is e itself. But in general, if you make n bigger and bigger and bigger, and you take an arbitrary r, so it doesn't have to be 100% with a year, maybe they only give you, 25% for the whole year. So 25% would have been 0.25. So in that case, what this will approach is actually, again, still the constant e, except it's raised to your r, except r as a decimal. So that's what you will see. So if I would take, so 1 plus, let's say 50%, okay, and made n bigger and bigger and bigger, then you will notice that the answer is going to be this. That's what it's going to approach as n gets bigger and bigger. And I actually did this so that you can see here, okay? So I set here, so different kinds of r, so 50%, okay, 25%, and notice, so this is still taking my n, so that's what it would be. So in this case, it's a huge number, and it is approaching. So in this case, since it's 50%, so it's going to be e to the 0.5, that's your r. And notice, indeed, that's what it starts to approach. In the second one, so that is 0.25, and that's exactly what it starts to approach. Okay, and that works the same thing if the r is actually bigger than 100%. What if it's 200%? Then it's going to approach e to the power of 2. All right, and that's what you will see, and so on. So you can, do this spreadsheet on your own. All right, so that you can play around with this. Okay. So now you have some sense of this e. You may or may understand exactly, like how this e comes about. So it comes kind of from the question of compounding money within 1 year. And compounding is certainly one application you should learn for exponential growth. In fact, I'll put up a playlist, okay, from the exponential growth and compounding up above there. And there you have it. Okay, so hopefully that is helpful. You kind of have some sense of this Euler's number and this constant, and it will be utilized if you continue your journey in math and sciences. All right, bye everybody. See you in a future video.